Welcome to day 37. We often talk about AI mimicking the human brain, this incredible network of almost 90 billion neurons. But how do you even start to build something like that? Well, it all begins with the simplest possible decision a machine can make.
So what is that? What's the smallest, most fundamental unit of thought for a machine? It's really just a simple yes or no, a single binary choice.
And by the end of our time here, you're going to understand something called the perceptron. It's the original artificial neuron, and it truly is the fundamental building block for pretty much every modern neural network out there.
Okay, so to get a handle on this artificial neuron, let's actually start with a human one. We're going to see how a simple decision we make every day can be modeled by its computational cousin, a binary classifier.
Let's use a really common example. Imagine you're trying to decide, should I go for a run? It's a simple yes or no question, but the process your brain goes through to get to that answer is actually pretty interesting.
Your brain almost instantly starts pulling in different factors or inputs. Things like, is the weather good? Yeah, let's say it is. Do I have enough time? Maybe not a lot. And how am I feeling? Feeling okay, energetic enough.
But here's the really important part. You don't treat all those factors equally, do you? You instinctively weigh their importance. For me, good weather is a huge plus, so I'd give that a really high weight. Time? Not as big a deal. I can always do a shorter run. And my energy level is probably somewhere in the middle. You mentally add up all these weighted factors to make that final yes or no choice.
And it turns out, this whole process of weighing evidence to make a simple choice is precisely what the very first artificial neuron, the perceptron, was built to do.
So here it is, the Perceptron. It was developed way back in 1957 by Frank Rosenblatt, and it's the simplest kind of neural network you can have. Its job is to do exactly what we just did. Take a bunch of inputs, figure out how important each one is, and then spit out a single binary decision.
All right, so how does a perceptron actually weigh the evidence? Let's pop the hood. It really boils down to three key things: inputs, weights, and something called a bias.
Here's how it works. First, the perceptron gets its inputs: weather, time, energy. Second, every one of those inputs gets multiplied by a weight. That weight just represents its importance. A bigger weight means it has more sway in the final decision. And third, we add a special value called a bias. You can think of the bias as your default tendency. Are you just naturally a person who loves to run? Your bias would be high. Do you need a lot of convincing? Your bias would be low. It's kind of like the starting point for your decision. Then all these pieces get combined. The perceptron calculates what's called a weighted sum. It multiplies each input by its weight, adds all of those up, and then finally adds in that bias term. What you're left with is a single number. But that number isn't the final answer just yet.
To get to that final yes or no, we need a decision rule. In biology, we talk about a neuron firing an electrical signal. For a perceptron, it's about whether that calculated number crosses a certain threshold.
So, we have our weighted sum. It's a single number that represents all the evidence. But we need a binary output, a yes or a no, a 1 or a 0. To get there, we need one last piece.
And that piece is called the activation function. For a simple perceptron, this is usually a step function. And the rule is dead simple. If the weighted sum is greater than some threshold, let's just say 0, the neuron fires and outputs a 1 for yes. If it's not, it outputs a 0 for no. That's it. That's the final decision maker.
Now, a single perceptron is beautiful in its simplicity. But that simplicity comes with a very big catch, one that actually stalled progress in AI for quite a while.
Here's the limitation. A single perceptron can only solve problems that are, in technical terms, linearly separable. What does that mean? It means it can only draw one single straight line to separate two groups of data. If your problem is more complex than that, a single perceptron is going to fail.
This is the classic example of that problem. It's called the XOR problem. You've got two classes of points here, the blue ones and the green ones. Just try it. Try to draw one single straight line that cleanly separates all the blue points from all the green ones. You can't. It's impossible. And that means a single perceptron just can't solve this puzzle. So how did the field get past this? The answer wasn't to design a more complicated neuron. The answer was to use more of these simple neurons, but stacked together in a very clever way.
The solution was actually pretty ingenious. It was the realization that if one straight line isn't enough to solve the problem, well, why not use more than one? The big leap was to stop thinking about a single perceptron and start thinking about a whole network of them.
And that brings us to the multi-layer perceptron, or MLP. You still have an input layer and an output layer, but the key difference is in the middle. You have one or more hidden layers of perceptrons. We call them hidden because we don't directly set their values. Their job is to learn useful, intermediate patterns from the data, all on their own.
And here's the magic. Look at how an MLP solves that impossible XOR problem. The first hidden layer might have one neuron that learns to draw this line and a second neuron that learns to draw this line. Then a neuron in the next layer learns to combine their two simple outputs. By working together, these simple line drawers create a much more complex, nonlinear decision boundary, and they solve the puzzle perfectly. This is the core idea behind deep learning.
And this basic idea, layering simple decision makers, is at the heart of almost all modern AI. When you hear about convolutional neural networks for images, or transformers like GPT for language, what you're really looking at are just extremely deep, sophisticated versions of this very concept.
So at its core, a neural network is really just a set of interconnected layers of these simple artificial neurons. Information flows forward, and at each step, it's transformed by one of these simple decisions.
So the key takeaway is this. Complex, intelligent behavior in AI doesn't come from one super genius neuron. It emerges from layering thousands or even billions of these incredibly simple decision-making units. It's the power of the network that creates the intelligence.